as you're getting settled, I asked that, so I think for the most part, everybody is set up. One of the challenges with setting up was that conda solving was taking long, as I said before. I think that's because we're all using the same Wi-Fi connection that is not that fast. So one thing that we might be able to do to improve that is if you, through your educational institution, have access to EduRoam, if you could switch to EduRoam Wi-Fi, that would be helpful. Not required, but I could see it being helpful for later in the workshop when we're downloading raster files or fetching raster files, making plots. So we're still going to be kind of depending on a Wi-Fi connection for this workshop. So if you can switch to EduRoam, please do. Okay. Also, if everybody can put down their green stickies, so that we're just starting fresh. Then, as you're getting your laptops out, please open each of these links in separate tabs, because we're going to be, especially have this table of contents open, because we're going to be jumping from episode to episode soon. Have the setup instruction page open, because we might refer to that later. In case you spent a lot of time setting up your environment, you may not have downloaded the vector files for this lesson. So if you didn't do that, no worries. That's the curl step that we showed. We're not gonna need that for the first coding lesson we do, episode 5. So we'll take a break after episode 5 to check in and make sure folks have installed all the vector files. But you still have the setup page open because we'll need to refer to that. And then, yeah, as I said before, open this Etherpad page so that you can take notes throughout as I'm talking, Chad is talking, chat with your colleagues. I think everybody's back for the most part. So let's officially get started after some setup. Cool. So I'm going to open the table of contents here. Cool. So let's learn a bit about each other. This is really helpful for me to kind of get a sense of where the audience is at. I think I have a sense just from helping some folks, but who here has written a Python script before? Cool. Who here has used Rasterio in a Python script? Okay, what about geopandas? Okay, cool. Who here has worked with Landsat or Sentinel-2 data before in a GIS or Python? Cool. Okay. Who here has reprojected a geotiff? Cool. So what was that? We're done? Yeah, yeah. We're done. You already know everything. No, we're going to show you how to do all this in Python. But it does look like there's a mix of experiences here in this room. Like some people have more programming experience, some people like have some more geospatial experience, some people haven't been exposed to some of these geospatial concepts before. So we are going to go through a couple of talky portions of this lesson. I'll try to get through this in about 15, 30 minutes or so. And so some of this is definitely going to be review. But yeah, let me just say that yeah, this carpentries link, it's always up. You can always refer back to these lessons and read more. Even if I'm going fast over these, you know, if this feels fast, you go back and read through these lessons. Yeah, so we'll start with introduction to raster data. So what formats should I use to represent my raster data? What is a raster? What are the main data types used for representing rasters? Talk about integers, floats, and what are the main attributes of raster data. So a raster is an image where every pixel is a georeference. So those pixels have values. Those pixels also have a resolution. So they represent, you know, a 1 meter by 1 meter area or 10 meter by 10 meter area.
So those rasters can have multiple bands. So you may have a one-band raster that has one array representing like a blue channel, or you may have 3 arrays in that raster representing red, blue, green. You may have 4 arrays representing like red, blue, green, NIR is near infrared. So we can use these rasters to make plots. So in this case, this is a single band raster representing elevation for a site, a forest site. Yeah, rasters can represent many other kinds of data besides optical data or elevation data. They can represent precipitation maps. Rasters can also be used to represent land cover categories. So there's categorical raster data, and then there's continuous raster data. So an optical data set like Sentinel or Landsat, that would be continuous. Your values would typically be represented by floats or like N16 integers. For continuous raster data, every integer is going to be representing a land cover class. So you might use something a little more minimal in size, like int8, that keep the integers categories. So let's just like take a brief pause, and I want you to talk with your neighbor. What are some potential advantages or disadvantages of storing a land cover map in a raster data set, maybe versus a vector data set? So you can add your ideas to Etherpad, advantages or disadvantages of using rasters for land cover data. We'll come back in like 2 minutes. So brainstorm, talk with your partner. Okay, and time. So, what are some thoughts out there? What are some advantages to storing data as a raster? Storage space. Okay.
It saves the vector data.
So vector data could potentially be like higher cost in terms of storage, you're saying. Okay, cool. And what are some other advantages? So higher detail. Yeah, okay, cool. Less expensive in what way? In terms of storage, cost to store, or what?
Okay, so here's kind of interesting. Two people said, you said raster data is less space than vector data. Did someone, or then, oh, that's what you also said. Okay, so you're.
And we can observe point line polygon, all sorts of features in a raster image, but there is a vector feature of it for each point line.
Okay.
Also, the raster operations, the raster calculations, those mathematics.
Yeah, okay, so raster supports some forms of calculations that vector does not, like array calculations can be really fast, whereas you can't do that with vector. And then there was also a point about raster being able to represent points, lines, and polygons, whereas with vectors, you might store those in separate files, points, lines, and polygons. It is possible to store them in the same file, but we'll get to that. Cool. So let's take a look kind of at the solution. I think we touched on a lot of options, but interestingly, one downside of raster data that's listed here is that the size can actually get very large as the resolution increases. So your raster might be the way to represent your data with minimal storage, or it might be more efficient to represent your data set as a vector for minimal storage. It sort of depends on the level of detail in terms of resolution of the raster and the complexity of the vector boundary. Little interesting thing there. Yeah, raster is good for continuous data. High level of detail is possible with higher resolution. And then we covered that cell by cell calculations, array calculations. One point I really want to point out, though, a downside to raster data is that the geotiff format, which is like the most popular format for representing raster data that we deal with in remote sensing, is it doesn't embed metadata very well. So if you have a time series of geotiffs, each of those geotiffs store metadata for that particular file, but there's not like a good format for like file or archive format for geospatial raster data that stores metadata for the whole time series. So we'll talk about like a solution that's that we have for doing that. I think that covers everything I wanted to touch on there. Any questions so far? Cool. So important attributes, spatial extent that the raster area covers is an attribute of raster data that can be represented by a polygon or a bounding box, typically. Resolution is another property that we've talked about. And the raster format that we're going to be using for the workshop is GeoTIFF, specifically a Cloud Optimized Geotiff. We'll talk about the advantages of Cloud Optimized Geotiffs, or COGs, later. And yeah, raster data multiband, as we discussed. And that multiband could be RGB, it could be multispectral, it could be hyperspectral. When we talk about hyperspectral, we're typically talking about more than like 10 to 15. Cool. That's raster data. Vector data. We'll talk about strengths and weaknesses again, and talk about different types of vector data. So we have points, like maybe gas station locations in the city. We have lines, maybe roadways. We have polygons, represent forested extent, or building footprints. So here we go. What are some vector types represented in this plot? Yeah, so it's like, I think this is kind of a trick question, because just looking at this plot, you may not know whether these boundaries of these states are lines or if these are polygons. So this could be a multi-polygon, or these could be lines. But that is definitely a point that like Fisher towers. So we'll learn how to inspect vector data in Python to actually determine is this a line or is this a polygon. You can do different things. We'll get to a lesson where we're calculating zonal statistics on rasters. So zonal statistics is like you have polygons that we need in your zone.
polynomials, where you want to calculate like mean or standard deviation. Polygons for that. Lines. Yeah, convert the lines to polygons. Cool. There's many vector formats. I don't pretend to know everything about every single format. Who here is like works with shapefiles? Yeah, so shapefiles are a really popular vector format. We'll be working with those today. Shapefiles are a little confusing. Like, who here is like ever looked at everything, all these different extensions and wondered what all these extensions do? Yeah, so a couple of reasons. So the dot shape file is typically what you would click on to actually open it in a GIS, or what you would refer to load it into GeoPandas and Python. Dot proj is like where all the coordinate reference info is stored. And to be honest, I ignore the other extensions, but they're described here. So there they are. If you want to read more about that, time we'll move on. Shapefiles, similar to rasters, have extent information typically embedded in the file, or there are libraries that allow you to compute that extent information. You can load in the polygon or the line. You have the object type is encoded. The coordinate reference system is encoded. We'll talk more about coordinate reference systems in a bit. Shapefiles, I guess in this .dbf is important in that shapefiles can also record like non-spatial attributes. Like say you have a shapefile listing all the rivers, and those rivers have names. They also maybe have species that are located in the river. The rivers might have width. And so this .dbf will record the non-spatial attributes and tie them to actually spatial coordinates for those. Okay. Yeah, very few formats can contain both raster and vector data. So yeah, vector data sets, they typically have one geometry type. You can have like GeoJSON that includes like lines, polygons, like geometry. But yeah, like you were saying in the corner here, that yeah, typically they're locked to one geometry type. Yeah, raster data sets can usually only use one data type, so like floats, 16-bit, 8-bit, and it makes standards for these formats easier to maintain. It makes writing metadata for raster or vector. Cool. So moving on here, coordinate reference systems. What is it? How do I interpret it? Coordinate reference system tells your mapping software where the raster is located in geographics. So it'll tell you the coordinates, and then it'll also tell you how should those coordinates be mapped. What I mean by that is, like, if we scroll down here, every CRS is going to include some components like the data, which models the shape of the Earth. So there's different datums out there that model the Earth differently. The Earth is not a perfect sphere. It's also not a perfect like ellipsoid. It's lumpy. And so you have to have a datum with ground control points placed on the Earth that are very accurately geolocated to build this model of the Earth. And so the most popular datum, at least that I tend to work with, that I tend to see out there, is WGS-84. There's also NAD-83. Anecdotally, I think I've seen NAD-83 out there more with like data sets coming from NOAA, whereas like I see WGS-84 everywhere else. But I'm not sure like who uses NAD-83. Okay, cool. The census. Cool. Thank you. And then, so besides the datum, the model of the Earth, you also have to have an understanding of like mapping this data. How should I take like imagery or vector on a curved surface and map it to some other coordinate space? So the projection is this transformation that takes an angular measurements on a round Earth to a flat surface. And there's many ways to take a curved surface and flatten it. And there's different trade-offs. So you might have a projection that preserves area really well, but doesn't preserve distance. You might have a projection that preserves distance, but doesn't preserve area. So projection will define that mapping, and will also define the units associated with that new coordinate space. So maybe it's feet, maybe it's meters, like UTM in meters. And there's different UTM zones that you need to pick and use depending on where you are on Earth. So in this workshop, we'll learn to work between projection and reproject data in Python. I guess additional parameters that you might expect are like the center of the map, and there might be others for particular projections. There's different projections for different planets that can get really complicated. But I really like this orange peel analogy. So a datum is the choice of fruit to use. It's the earth and orange, a lemon, a lime, they all are lumped in different ways. And then how you peel that fruit is your projection. So how you choose to flatten. You can cut up the earth orange in many different ways, and you might preserve like often area, but distances are messed up. So there's many ways to do it. UTM like cuts the earth, puts it on a cylinder and then cuts it further. So there's many different ways to cut up the earth orange. Which should you use? It depends on your application. So as we said, minimal distortion, preserve the aspect of the data that we care about. So how do we describe coordinate reference systems and coordinate standards? Who here is used EPSG or seen EPSG? So this is what does it stand for? It's maintained by the International Association of Oil and Gas Producers. It's a really common shorthand way to refer to many projections, but not all projections have a code. So it's a 4-digit number. So 4326 refers to a geographic projection, meaning the units aren't lat-long coordinates with the WGS data. That's one example. You can use epsg.io for finding new projections, looking at the details. Another standard, a different way to represent projections is well-known text. I'll just leave it at that. Another way that we'll look more at the workshop is Proj. And so Proj is both an open source library for storing, representing, transforming coordinate reference systems, and inspecting coordinate reference systems. And they also have their own standard Proj metadata standard for reference. So there's different keys in this Proj string for the projection of the data, the zone of the data, if the projection has a zone like UTM, data to use the units. And I guess besides the datum, there's an additional parameter on like how the Earth's roundness is calculated, which I would say that it's related. Okay, so here's a project for string example. I think this one's relatively self-explanatory, but there's keys for zone, datum, and then the units equals M means units are meters. Format interoperability. There's a library that is very important that we're not really going to use directly today, called GDAL. Some people say Doodle, some people say Goodal, or there's all these different ways to pronounce it. But GDAL is a library written in I think C++ or C that powers a lot of geospatial software, including Rasterio. And we're not going to touch it today, but just know that like GDAL is kind of like underlying a lot of like the Python libraries, geospatial Python libraries that we're using today, and allows you to translate between formats, do reprojections. There's resources here for like choosing the right map projection, which is useful. So check that out if you'd like. And I think we're at the 30 minutes I wanted to be at, going over these talkie lessons. I'll just wrap up with what the geospatial landscape, what programs and applications are available for geospatial data. I want to go over this just because I think some folks might be familiar with GIS applications, but not as familiar with like Python landscape or R landscape. So we'll talk about this a little bit. There's open source software. You don't have to pay to have a GIS if you want to. So QGIS is a really popular tool for managing, processing data, making maps. Very powerful. There's other GIS options here. QGIS is powered by GDAL largely. There's commercial software. I grew up in undergrad like Esri and ArcGIS, very powerful tool, similar to QGIS. There's others, maybe they specialize in remote sensing, like Envy or Earth Imagine. And then there's online cloud computing options. Google Earth Engine, I'm sure folks have heard of that. It's a very popular option for GIS in the cloud. ArcGIS Online, I'm not familiar with, but I've heard it's very powerful. And then PanGeo is a community organization, open source, that supports the development of Python-based tooling for GIS and just spatial analysis in general. So maybe not necessarily geospatial, but spatial. So we'll cover kind of all of the tools in this stack later, but like PanGeo sponsors the development of Xarray, rioxarray is related to Xarray, a variety of plotting libraries there, DAS for parallel computing. Yeah, just briefly, what are the benefits of a tool like QGIS or ArcGIS versus doing something in Python? Benefits of a GUI are that all the tools are laid out in front of you. Complex commands can be easy to run, potentially, like point and click. You don't need to learn coding language. And the cartography and visualization can be more intuitive. So it might be easier to build a map in a graph. Downsides of a GUI, and I really want to highlight these because I think these are going to come up in your research years, is that low reproducibility. You can't record your actions in GIS and then replay them or publish them for others to read. That is significant because I think nowadays folks are expecting more and more to be able to run your research in like so this is, I would say, a big con. GUIs are not designed from the ground up for batch processing files. So slow sometimes. Limited ability to customize. So maybe they have a lot of functions that are easy to use, but they don't make it easy to build your own function, solve your like specific problem. Sometimes like the interface to me actually nowadays is more intimidating to me to open QGIS than it is to open Jupyter Lab and go to Python because oh my gosh, there's so many buttons. So there's still a learning curve, just as there is a learning curve. Cool. So what are the packages we're going to use today? We're going to use the Shapely package for managing geometries. GeoPandas is built on top of Shapely that combines a tabular data structure with Shapely shapes. So who here has used Pandas for tabular data? Great. So Pandas is like your Python Excel. And then GeoPandas is like your Python Excel that understands geo. And then it's similar if you've used R to the SF package, spatial features package. We'll use GeoCube as well for converting vector to raster data. So rasterized vectors. Rasterio and rioxarray for working with raster data. Talk about those more. And then matplotlib for plotting. NumPy we'll use a little bit for statistics and with arrays. There's other scientific Python packages. Formats that are important to know about are listed here. I'll breeze over these a little bit. But just stop to say, like with COGs, we're going to be using some cool features of COGs. We're not, again, as I said, we're not downloading geotiffs today. We are fetching URLs pointing to COGs sitting on the clouds and loading them into Jupyter. And COGs are cool because they support fetching only what you need. So I only want to fetch part of a geotiff file that I need, like a particular upper corner or a particular area of interest cutout. They're also cool in that they support parallel reads, so it's fast to fetch them. Yeah, you can also fetch lower resolution representations of the COG. So maybe I don't need a 10-meter centimeter. Maybe I just need a 70-meter image. I ran into this with Sentinel-1 where I only need 70-meter resolution to delineate oil slicks in the ocean. So you can use COGs to fetch these lower res versions, and programs run faster, lower cost to store, etc. Cool. With that, let's get to coding. So Chuck is going to start us off with episode 5 on how to access cloud optimized satellite imagery geotiffs in Python. We're going to cover these questions and objectives. Before we start out, Chuck, we'll connect your laptop here so that you can sit. Feel free to use mine too. You got yours. Cool.
Yeah.
So I'll I think you'll have to get on the Zoom and share the screen.
Yeah, I got it.
Perfect. So I'll skedaddle out of here. Close this. Now, and just a reminder, as Chuck's being connected to the Zoom, stop screen sharing. If you need help throughout, put up that pink stick. Okay. And if you need help right now, put up that. I'll be walking around. If I don't see you, just like raise your hand. The room's a little dark. So if I don't see you, cool. Yeah, here you go. Yeah.
Yeah.
Yeah. Oh my gosh. It's such a good question.
The question was, COGs have the same file extension as regular geotiffs that are not cloud optimized. So how do you tell it's a COG? The unfortunate answer is you have to use tools to figure that out. I wish it was easier. You can't just open the file and look at it, or there's not a particular extension for a COG. So you can use GDAL-info to check if something is a COG. You can Google how to run that command and check it. There's probably ways to do it in QGIS as well. But when you installed the packages with Conda, you might have installed GDAL. So you could try running GDAL-info in your terminal. Check that out. We're not going to be doing that today, but just know that that's Googleable and you can run command and check. And then I would say that too, where do you get COGs? COGs are provided by a variety of providers. So we'll cover different places that you can access cloud optimized geotiffs. NASA provides various endpoints for shooting COGs.
AWS is also hosting a lot of remote sensing data sets nowadays with the AWS Open Data Program. Microsoft is as well with Microsoft Planetary Computer. Google Earth Engine, I think, is now using COGs for all of their archives. So you can expect that all of those are going to be Cloud Optimized Geotiffs. They have that .tip extension. They're like on the cloud.
All right, any other questions? Good. Okay, so after our Python setup marathon, so make sure everybody is in a good place. Did everybody get to import rioxarray? Does that work for everybody? Okay. All right, the rest is easy. So what we're going to do is, so Ryan just went over the first four of these sections, these episodes. We're going to start with episode 5 in terms of coding. Basically, we're going to figure out how do we actually find data that we want to work with. So how do we find satellite imagery? We're going to be looking at satellite imagery, as Ryan mentioned, the Sentinel-2 data. How do we search for it? And then how do we actually get the data to do something? So let's first take a look at the way for searching for data. So how many of you are familiar with the STAC specification, Spatio-Temporal Asset Catalog? Oh, okay, wow.
That's exactly what I would expect. Yeah.
Cool, cool. All right. Let me say whatever I want. All right, so we need a way to look for data. So the Spatial Temporal Asset Catalog, the STAC catalog specification, is something that was created, it's fairly recent, past few years. Yeah, a standard created to allow us, regardless of the data, to have a consistent means for discovering and accessing this data. So what we're going to take a look at first is, so the specification gives us a consistent means for defining this data, what it looks like, shape, basically the shape of the data, the metadata. It's actually a metadata specification. So we're not talking about the file formats that Ryan has been talking about in terms of shape files and geotiff and all that. So this is about specification for the metadata about all this data. So regardless of the data format, where it exists, it's a consistent means for being able to publish, construct metadata, publish that metadata, make it searchable, and provide information for them accessing, finding that data we want so we can access it. And as Ryan said, we're going to be looking at typically catalog entries that are referencing Cloud Optimized files, because shift has been away from typical workflow of always downloading the data you need. Of course, as the technology evolves, we're getting larger and larger sets of data and larger individual files. And it's not really feasible if you're doing anything with a significant volume of data to try to download all of your data locally, your laptop, computer, and of course, it's not really scalable. So we want to have data in the cloud so we can scale up any sort of computation you want to do against that data. So let's take a look at this STAC catalog. We're not going to look at the specification itself, but what we're going to do is, again, as Ryan mentioned, we can have GUIs for doing things, and we can do things programmatically. So we'll take a look at a GUI interface for being able to browse catalogs. But our intent here today is then to look at how we do the same thing programmatically in Python. So instead of going out to this GUI, which we'll take a brief look at, see some screenshots, how can we do the same thing that we're doing in the GUI, but programmatically, and then also that would allow us to automate anything we want to do. Because as Ryan mentioned, trying to automate some sort of process where you're pointing and clicking through a GUI is generally not feasible. So let's first take a look at, well, what are these catalogs? Look, how do we even know what catalogs are out there? So catalogs of metadata. So there are a few links here, but if it's actually is this readable from the back? It's good. Okay. Let's take a look at this index. So we have this stack index. And this is basically a meta catalog. It's a catalog of catalogs, if you will. So it's a big index listing all of the stack catalogs. So there's the stack specification, which we won't go into, but that's the specification that says what your catalog and your metadata in your catalog needs to look like so that it's consistent across the board. And then there's the catalog itself, which is the actual metadata that you've stored. And this index points to various catalogs of data that are openly available. So we're talking about all sorts of open data. And if you notice here, there's a big submit button on the top. So if you have data that you want to make available to others, you can submit it, make it part of the stack index so that it's now visible to others on the index. You can see there's all sorts of catalogs of metadata on all types of data. What we're going to be working with is no, it's near the top here. Yeah, this one. So we're going to be looking at Earth search. Now, one thing is there's sort of the chicken and the egg thing is how do I know which catalog to look at? So sort of you kind of have to know which catalog you want to look at. So there's not really a search, like a super search across all catalogs to find the data you want. You kind of have to know which catalog has the data of interest for you. Today we're going to be looking at Earth search. Okay, and this is something put out by Element 84. They maintain. Notice here we've got our Sentinel-2. We'll be doing 2A today, right? So you can also see that Element 84 publishes several collections of data. Data here. Go over to.
I just want to kind of shout out the stack index because there's some really cool data sets there. So you saw Capella space. I think that's like sub-meter radar imagery. Play around. Yeah, there's a lot of cool stuff out there.
Okay, and then we have what's called a stack browser. This allows us to go browse specific catalog. So there was our index, which just kind of lists all the catalogs are out there. And then we have the stack browser that allows us to choose a particular one of those catalogs and browse through it. What we do is come over here. Search. Okay. Now we're looking. Okay. Is that readable back there? Good. Okay. Question?
Is it Earth only data, or do you also have data?
For the planets? Oh, that's a good question. Question. Brian probably be able to answer that better than I. So the question is are these catalogs Earth data only?
So, like, are you interested in data for other planets?
Yeah.
There might be stack. I've seen that discussed.
like on GitHub, but I'll just say that it's probably early days for like other planetary data. And I honestly,
Yeah, it's primarily Earth focused, but yeah, I don't think there's anything in the spec that would prevent.
I don't think there's anything in the spec that would prevent it, because there's, as long as it's using like the proj projection standard or well-known text, you know, you can have a projection that defines like datum for another planet, so that should be supported, and then that should work. You just may not see anything in stack index right now for that, and stack index doesn't actually record all stack catalogs. Like not everybody submits to stack index, so you could be further.
Okay. So now you might notice here the URL shows Radiant Earth up here. So Radiant Earth is just the producer of this browser. The site itself that allows you to browse around. But the data we're looking at is just metadata that adheres to the stack specification. So it's also set up so that it's very browsable, and linked data is linked, so you can follow links and get to different things within the metadata itself. So Radiant Earth is just hosting this browser, the stack browser, and the Element 84 is the maintainer of these particular sets of collections we have out here. So we're going to look at Sentinel-2 level 2A. And what we'll see here is that this is the whole Earth. And then within this collection, so these collections typically represent various satellite constellations. Right? So it's the Sentinel LA, and then in this case, it's the level 2A data from Sentinel constellation. So what we're going to want to do is
Scroll down in the browser and like kind of look at these attributes.
Yeah.
So click on a C.
Yeah. So what we have here, let's look at one of these. So within this, we have an item. Okay, let me go back up for a second. So along the right, you can see thumbnails. So these are all items within this particular collection. So if we drill down into a particular item, we can then see, of course, which collection it's coming from, but we can also see all sorts of metadata about this item. So we see metadata over here on the right. And then within this particular, yes, question.
Sorry, I might have missed it, but I know that, so on the course page, we have the GitHub, like, which is
The
the
stack.
stack browser.
Yep.
Is that like something we could have built from within the stack index?
Yes.
Or
No.
Oh, the stack browser itself.
Stack browser. Can you show where the link is to stack browser?
Yeah, we have the stack browser here.
yeah, I mean, I was just wondering,
How they're
like,
related.
what? Yeah,
Yeah, how do we know to go to Radiant Earth?
yeah, like which one would you go to, or how are they different?
They, I believe, are maintained by two different groups, so they're not super related. In terms of like, there's not one company or group.
Okay, so it's basically two different places to access the same data.
Yeah, stack browser is like using stack index to like show all the. It's like it's a way to actually step in and visually browse like images in different catalogs. So it's using stack.
That's a good question. Yeah, there's no obvious link. How do we know to go to Radiant Earth to actually browse this stuff from looking at the index? Yeah, there's no obvious link here, but you can go out here, stack browser, the Radiant Earth stack browser is the first one. good question. Sometimes the connections aren't obvious and takes a little bit of knowledge. Okay, so
Here, Chuck, I would say let's browse an item.
okay. So we're looking at an item, and each item has a number of assets. So we can see here, and we'll get to see what this looks like. So we'll look at, take a quick peek at metadata that actually allows the browser to just represent this visually in a nice GUI here, instead of looking at JSON. Okay, so again, we don't want to drive our workflow through a GUI because we can't. It's not repeatable. It's not amenable to batch processing, automation, scalability. So what we're going to do is, and I'll try to flip back and forth so you can see what things look like in the GUI and how we're going to do the same thing programmatically in our notebook. So let me activate. So you all should have already done this. So hitting this for. Okay, so geospatial lab. Okay. All right, so I think everybody that is that readable from the back? Larger, good. Okay. So I believe you all were able to do this. Hopefully I can do this. Takes a few moments here to import rioxarray, but at the moment that was just kind of a test to make sure that our notebook sees all of the dependencies that we installed in our environment. Okay. Great. So let's take a look. How do we now programmatically deal with stack catalog? First of all, we need to know the URL of catalog. So if we go over here, we go up to our collection. So within the browser, the stack browser, we're looking at the collection that we're interested in. So if we click the source button up here, okay, this tells us the URL we're going to be using to access the data that we're actually looking at in the browser at the moment. But this allows us to access it so we can grab the data, deal with it in our notebook. So part of this, what we really want to do is we need to take the first part of this. I'm going to try to remember to type all of this out so that everybody can keep up. So what we want to do is first grab our URL. So we're going to need the base URL that we're going to be dealing with. So first search. Before this is the base URL. So this is the base URL for any of the collections that we want to access that are maintained by element 84. Okay. Now what we're going to do is equivalent to here. So here our client is our web browser. Okay. I'm going to get confused between stack browser and web browser, but referring to the web browser here as our client for retrieving this data, we also need to create a client in our code to be able to retrieve this data programmatically. So So we're going to use the libraries. One of the libraries that we have in our environment now is called pystac-client. So what we're going to do is use that. We need to import a client class so that we can now create. We're going to create a client. Now, again, this client is equivalent to our web browser as being the client. And we use the open URL function and that API URL for the element for catalog. And let's see, because I am open. Okay. All right. So now we have a client that's going to allow us to start looking at this particular or grabbing a particular collection from that element for catalog. Okay. So we can see here, it says it's a stack API, public data set from AWS. That's the other thing. So the data itself, the catalog metadata, and the metadata points to actual data that's sitting in the AWS cloud. Now what we want to do is we want to take a particular collection. All right, so how do we know how to access the collection? So let's go back to our Stack browser. And let's look at the source again. So in this case, you can see here at the end of this URL, we've got collections/sentinel to L2N. So that is the name, the key that we need to use to say, hey, grab us this metadata items for this collection. Okay, and now we're going to tell the client to actually grab this data. Now I think, as Ryan mentioned already, but I'll just sort of review. So a Cloud Optimized file is something, the reason it's called Cloud Optimized is because when we fetch data from the cloud, if we have providers that support fetching range of data so that without getting into too much detail, but of course the HTTP protocol that we use for URLs, this protocol allows us, there's something called a range fetch. So rather than say, hey, go out and grab an entire file out of this web address, we do things that say, hey, only grab me a chunk of this file. So if you know the range, if you got your file is so many bytes, but you know you only need a certain range of bytes, that's what these Cloud Optimized formats allow you to do, is that if you know which chunk of data you need from the file, you might have a multi-gigabyte file, but you don't want to be downloading that much data all the time. But these Cloud Optimized formats allow you to know specifically which part of that file you need, a region, a particular time frame, a particular resolution. Again, as Ryan mentioned, some of these Cloud Optimized formats allow storage of same image at multiple resolutions. So maybe you need just a lower resolution file. So figure out where that is. And again, you don't have to figure out where this is. The libraries that know how to read these Cloud Optimized files know how to read the index that's part of these files and tell the library exactly which part of the file to grab for a particular resolution image, particular part of the image that falls in the bounding box, for example. So that is the advantage of these Cloud Optimized formats. Just grab chunks we need, save bandwidth, save time, save money if somebody's paying for the data transfers. So that's what we're dealing with today. We're going to be looking at grabbing Cloud Optimized files. But also what we need to do, so as I said, we might just want something that's files that are intersect or are within a particular bounding box. So what we're going to do is take a look at a particular point. The point in Amsterdam, randomly chosen. So what we need to do is, if you recall, Ryan mentioned Shapely is another library we have in our environment. So we're going to, Shapely allows us to define points, all of our points, lines, polygons, multi-polygons, all those sorts of things. So we're just going to point, we want to define point, and we're going to go grab some data that intersects this point of interest. And again, this point, I believe, is point. Now you notice we have this point, and if we tell our notebook to display this point, we see a point. Nice visual confirmation there. Okay, so now what we're going to do is, using the element 84 catalog, we're going to say, give us this Sentinel L2A collection, but search within that collection only for items that intersect with this particular point. So we're only going to get back a list of images that. Move your mic. Move it up. How's that?
That's not even on.
No, I think it.
Oh, okay. Yeah. So project louder.
Yeah.
And then,
Sorry, mic died. Can you hear? All hear me okay in the back?
even louder.
Louder? Okay, can you hear me back there? Good? Okay. How's that? Helps to have batteries that aren't dead. Okay. Okay, everybody, any questions at this point?
Does this point indicate the normal XY coordinate or geometric coordinate?
I think this, that's a good question. I think this is probably a lat long. Long last. No, it's lat long. Okay. So what we want, anything else? Guys, what we so far? Is my typing slow enough? Making enough typos? Now, again, everything I'm typing here is in the lesson. All right. So if I'm going too fast, you can tell me to slow down, but everything's in the lesson. Okay, so what we want to do, in fact, let's just go back to the catalog. So here's our collection. So this is the collection we're going to get the metadata for. And these items are what we see down the right side. These are all the individual items. So, and we can see all these basically thumbnail images that get put up here. So what we want to do is programmatically say, give us those items on the right that intersect with this particular point. So we'll use the client. Client has a search function, search method, where we tell it what are the collections that we want to search. Now you can specify multiple collections, but in our case we're just looking at one. Still have to specify it as the list search method, and then we want to say, all right, point. And since there may be many, could be hundreds, thousands, we'll just say, hey, just give us 10. Don't ask me what order they would come back in. I'm not sure this would give us any particular order. Okay. On the search, and let's take a look at what we have. So what this search will do is, even though we say just give us 10 items at most, we can still figure out how many actually match this search. Okay, so there are actually 868 items in this collection that intersect with that particular point, but we only got 10 of them. Right, so if we look at, we need to get our items out of this. Just 10, right. Out of the 868 matches, we just grabbed 10. Yeah, question? Good.
Yeah.
Okay.
It's like chemical.
So let's just take a look at what these items look like.
So there was a question about like why are there so many featured search items matched? Sure. Just this is Sentinel-2. So Sentinel-2 like images the whole Earth like every 5 to 10 days, something like that. So
Yeah.
there's many images from many different times that intersect this.
Yeah, what's the time? Yeah, it's many years.
It goes back to like 2015.
All right, so let's just take a look at what these look like. Okay, well, that doesn't really tell us a whole lot, but what we can see is if you look at these IDs, it just prints out the ID for each item. But again, go back and look in the stack browser. That's exactly what we see over here. We see the ID. We get a little thumbnail and all that extra information, but same thing we're getting back here. So under the covers, the stack browser is basically doing the same thing we're doing in our notebook, but it's then connecting it to a web application. So it's visual presentation here. Does that make sense so far? We're basically just kind of replicating what this browser is doing, but we're doing it in our code. So we can make it repeatable. We can scale it up. We can do all sorts of interesting things that we'll be getting to. All right, so how do we look at more than just the ID? The ID doesn't give us a whole lot of information. Well, let's just grab one of these items first. I'm just going to grab the first item out of our list of 10 items. And we'll look at all sorts of things. So we can look at, is the bottom of this visible? Am I in the way for anybody? Up a little bit? Okay. All right, just good. Oh, so you can see the code. Good. You want more? More.
Yes.
Okay, again, this is all in the lessons. So if you get behind. Yes, so the question is there a way to download the most recent 10 images? So one thing that we'll do is, actually, I'm not sure, we may get to it in one of these exercises, but as part of the search, you can give it various search criteria in terms of, date time. In fact, there is an example we'll see, you can specify date time range. Depending on the provider, stack provider, so we have L94. Depending on whether or not they implement the full stack specification, you can also provide all sorts of criteria in terms of sorting, whether you sort it by date time, so you can get most recent first, so sort it by date time, descending, then just grab the first 10. I believe these, it's a good question. I'm not sure if these are. The question is these 10 that we grabbed here. So even though we saw that there are 868 that matched, the 10 that we grabbed, because I said grab only 10, what 10 are these? Are they just random? Are they?
Yeah, the last one. July 11, July.
Yeah, you see, oh yeah, that's right. So it looks like, and off the top of my head, I would have to look at the documentation, but it does look like these are being by default. Yes, yes. There's a date time option. That's if you want some particular. Yeah, if you want some previous date time range in the past. But if you don't specify anything, it looks like here default may be just giving you a reverse chronological order. Absolutely, yeah. So the question is, instead of a point right here, we're just intersecting a point. That can be any sort of vector, yeah. Point, bounding box, polygon, multi-polygon. Yeah. Another question. I'm sorry. Say that again, please. Yeah. So these are the items that we're seeing here, and we'll go into. We're going to take a look at some more of the details. So this is our collection that we're looking at, and we look down along the left. These are the items. Sorry, on the right. Left here. These are the items in the catalog. So if I go into one of these, which I took a brief look at earlier, you can see here there are various attributes of the time of it, what instrument, what the constellation. So we know we're looking at Sentinel-2A. So this is an image captured from Sentinel-2A at this time. I think, as Ryan may have mentioned, this is surface reflectance data that we're looking at. So you can see here we've got some keywords indicating that. And there are various types of things that are various assets that this item represents. So an item is really just a group of files related to a particular data capture, a particular time and location. And we'll start to look at is what these individual assets look like. So you can see here, we've got, oops. You can even see we've got files for all the different bands. So we'll start taking a look at these. These are all individual files, represent different band information. Okay. All right. So we try to go for another few minutes here. So we do an exercise so we can break on time at 12:10 for lunch. Okay. All right. So. All right. So. As we can see here, yeah, we're getting items. So if we look at one, what are some of the things that we have as an item besides its ID? So we can calling back to what I was just showing for the item, we see certain attributes like when it was captured. So if we look at time. Okay, you can see that this particular item, which really correlates to the ID at the top of that list there, you can see that this was captured on July 11th here. Okay, there's also all sorts of things. Let's take a look at the geometry for this. Okay. So this particular item is polygon with these coordinates. And let's take a look at, there's all sorts of properties as well. So again, remember, this is all metadata that we're looking at. You can see we have all sorts of properties that come along with this item. Yes. Yes, so the image itself, the question is we specified a point, but why are we seeing a polygon here? So the reason is because what we've captured, what's been captured by the satellite, are polygon images, okay, that intersect with that point. So I was using that point only to do a search and say, hey, give me everything in this particular collection that intersects with this point. No, this is what's captured. This is the metadata that's out in the catalog. Okay, so we can create a polygon and instead of a point, say, give me everything that intersects with a polygon. But this is the data that's come back to us in the catalog.
Are they taking an image or we're taking something like image, right?
Yes, so this is it's a good question. So the question is about images and what does this polygon have to do with our images? Is that the question? Yeah. So that's a good question. What we'll see is that but Ryan, correct me if I'm wrong, but the images that we're going to be getting later will fall within this. They have the same shape as the polygon. Is that right? So this is at the top of the item level. Assets.
So the item geometry describes the spatial extent of that specific satellite seed. So the footprint of that specific Sentinel-2 scene. Another Sentinel-2 item, like if you look at the 6th item or the 5th item, might have a different footprint.
Okay, so you can see I have all sorts of properties here. One that might be of interest here is cloud cover. That's in percent. So this particular image is 61% cloud cover. But also all sorts of metadata comes on. Yes. Question.
How would we go about understanding output, to know that percent?
That's a good question. So as part of the, I'm not sure about time to drill into this, but basically as part of the stack specification, you can also have extensions. And that's, if you notice here, we see this EO : prefix. So this is the Earth observation extension of the stack specification. So if we'd have to go look at the documentation for the Earth observation extension to stack, and that documentation will tell us that clouds have a property. So we can maybe come back to that later, but for the sake of breaking on time, we'll continue on because there's a brief little exercise to have you guys do before we break. Okay. In fact, I think that's a good point for the exercise. So. Okay, now let's take a few minutes to work on this exercise. Basically, it's going to be doing something very similar to what we just did. We'll just come back to review what we just did. So if you recall, we have our client. So we already have our client. We don't need to create another client. But what we want to do is we want to create another search, like I did here, but we want to make the search such that it meets this criteria here.
Can you increase the size?
Yep.
Couple.
Good. Okay, so we're gonna do another search. Take a few minutes to just construct another search again. Similar, we're gonna do this sort of thing. We're gonna call client search. But what I want you to do is determine what you need to pass. So do the same collection. But what else do you need to pass so that instead of just intersecting that point, how do we create a bounding box that intersects buffer of 21 degrees around that point? And of course, specify date time between these two dates. So we have a 10-day period that we want to search for. So we're giving a particular period instead of just giving us the most recent 10. And then making use of this cloud coverage query. Now this is not obvious. It's a little tricky. So some of the stuff that we do, you have to be able to go look at the documentation. So
Can you show them the cloud? And then I would say, if you're wondering, how do I pass a bounding box to client.search? You can go, I would say this is a good time to practice going to the documentation of pystac-client, Google that, and look at the documentation for the client.search function. That'll tell you what you need to know. So let's spend 5 minutes on this exercise, then 5 minutes for you to go over it, Chuck, break for lunch at 12:15. And yeah, it's okay if this is a bit of a challenge. It's okay if you don't get it right away, because it requires some digging. But talk to your partner, pair up, put up a sticky if you have a question, and Chuck or I can come around. And I would show them the how to do the cloud.
so give you a little bit of a leg up here. So we're gonna keep the same collection. You need to determine how you want to create a point, a buffer around this point.
Make it about passive bounding
bounding
box.
box.
Yeah.
And then to give you a, should I just show the query? So
Yeah.
the query, this takes some digging through the documentation. So the query for we want less than 10% cloud cover. So this is not obvious. So EO, so as we saw in the properties up above, the name of the property is EO:cloud cover, and if we just say less than 10, that will give us a cloud cover. So
And I think let's do
less than 15.
that.
Yeah.
Oh,
Oh, is it?
I forgot to do it.
Okay, all right.
So this is important for later. Do less than 15 here, even though the exercise text says 10.
Yeah.
Do less than.
Didn't sync up the text with the solution.
So maybe there's a way, Chuck, could you like keep this like code on the screen, but then also show so they can see like the exercise challenge. Go back to maybe like keep one on the left side, one on the right side. Sorry.
Do this.
And then with the sticky system, put up a green once you've completed the exercise. Copy that. You should know you've completed the exercise if you're able to look at the items in your use. That's using the bounding box instead of the.
Is that all readable from the back? Sorry, this might be a little misleading. So with the bounding box, we're not going to use the intersect. Separate. Instead of intersects, we're going to use box.
Check out the documentation, figure out how to specify a bounding box. What has
Okay, let me see if I can. So if you search for, you go search for pystac_client. You want to go look for the documentation for this client, this search method. So search for pystac_client. Should be a link to the API documentation. Click through to that and search for search. If you search for search, open paren. That should take you right to documentation search. Either manually construct your bounding box 0.01 around that point, or I'll show you how to programmatically follow that.
Yeah.
Okay, I'm gonna give you a little bump on the V box. If you're having trouble with that, bounding box. Yeah, good question.
How
Yeah, let me show you. I'll show you this because if you're not familiar with the Shapely library,
But you shouldn't be. We assume you're not. So yeah,
That's
this is meant to be a big challenge where like you look up things and figure it out, and yeah, it's okay that you don't know.
so there's a very convenient way to give us this 0.1 degree buffer around our point. There's an actual buffer. Good. Okay, and then we want the bounding box. Sorry, bounds gives us this bounding box.
Oh, you
Go. Okay. So instead of trying to figure out how to hit all those points, that does it for us. So then we can say we want to use this bounding box as part of our search criteria. Instead of intersection with the point, we're just say everything that falls within this bounding box. Actually, you know what? I think we might have a. Should this be box? Because I'm doubting myself. Intersect should be any polygon or any vector. We'll see. We'll find out.
try to run it.
Yeah, we'll see. We'll see what happens here. Now, date time. Again, if you manage to pull up the documentation, you'll see that the date time keyword argument here allows you to specify an ISO date. ISO bounds can be open-ended. There could be closed on one end, open on the other. But for us, we're looking for closed interval of March 20th slash March 30th. Right now, I'm doubting myself if key box or intersects is what we want here, but so search. Let's see. Search match. Okay. So it is key box. Okay. Out of curiosity, though, you want to see if I can do intersects?
Yeah, I want to see what.
Let's see what happens. Lots of intersects must be of type non-string dict or object. Okay. Yeah. Yeah, it doesn't like it. So it is debox. However,
What points is only
sorry?
Sorry.
Yes. It does, but I think, let's say if we take a look at this, so the question is why can we not use Gbox with intersects? But if we take a look at okay, so it's just a tuple. So it's not coming back as a polygon. So if we were to convert that bounding box from a plain old Python tuple to a polygon, then we should be able to use it with the intersects keyword. But it's a good question. My assumption here would be, though, that whatever intersects that bounding box, because that bounding box is very small, so there's certainly no image that falls within that bounding box. It's got to be using an intersection to cover. Okay, so let me move some of my cruft here. Because what we want to do is let's get everybody. So what we'll do is we're going to wrap this up for the moment, so we can break for lunch. But what we'll do is when we come back, I'll make sure that everybody is able to get this working. Because then what we're going to do is we're going to save the results to a file that we can then use. Okay.
Sweet. Let's go to the dining hall for lunch, right? Because then, do you have any updates? 1 p.m. So 40-minute lunch, a little tight, but should be enough time. Yeah, we'll get started at 1. Hey, Kazem, what do we do about the Zoom?
Why don't they?
Kazem, is it safe to leave your stuff here?
No, actually,
Take your stuff. Take all of your stuff. That's the guidance.
take your stuff. If it's, okay, wait.
Can someone stay here and watch it?
If it's too much, just go for it. I'll stay.
All right. Do you want me to bring you food? Or?
No.
Okay. All right. So new guidance is if you must leave it.
You can't leave it. That's fine.
You can't leave it. You can't leave it. Check. I'm just gonna go to the bathroom.